So, first of all, thanks very much to the organizers for all the hard work they've done and in particular for the invitation to me to speak here. I want to first spend a moment explaining why I've been working on the problem of perturbative string theory. So, as I've explained here, I view the foundation of string theory as a sort of tripod where the three legs are perturbative string theory, by which the subject was discovered, and the various kinds of non-perturbative results, both the web of dualities and also the gauge-gravity duality. But there's a certain sense in which perturbative string theory is the first among equals, because it gives the foundation that you need in order to have a chance of studying the non-perturbative results. Often, if you look closely, you find out that what we know about the different types of non-perturbative results ultimately requires making contact with something about perturbative string theory. So, 25 years ago, to me, it seemed that perturbative string theory was sufficiently well understood. But in the meantime, so much progress was made in the other two areas that the foundation came to look a little shaky by comparison. So that made me want to work on clarifying some of the fundamentals. Now, there only are 25 minutes, so I decided I only wanted to explain one thing, and I wanted to explain it thoroughly, and because we've been working hard all week, I wanted to pick something that was fun. The only trouble is I can't guarantee it's fun for you. I can only say that it's fun for me. So I'll concentrate on explaining some basic facts about space-time supersymmetry in superstring theory in the RNS formulation. Although the particular story I'll explain also has an analog in the pure spinor version. The points are elementary, but in a sense they're easy to miss, and if you do overlook them, you run into the complications that actually made the literature of the 1980s complicated. So we're going to start by orienting ourselves with bosonic closed strings. We're going to discuss gauge invariance for bosonic closed strings. So first we're going to start just with matter fields. So V will be a 1-1 primary state constructed from matter fields only without the ghosts that represents a massless graviton or B field mode. Now, some modes are pure gauge. The pure gauge modes are the modes that, in the language of conformal field theory, are descendants. They're L-1 or L-tilde-1 of some W, where W is a primary of the appropriate dimension. And gauge invariance, getting a sensible theory of gravity, means that the pure gauge modes have to decouple. So let's discuss how you prove this decoupling. Using the operator state correspondence of conformal field theory, V corresponds to a 1-1 primary field or vertex operator, which I also will call V. And since it is a 1-1 primary, it can be integrated over the string worldsheet to describe the coupling of the state in question. Now, what if V is pure gauge? In terms of the vertex operator, the fact that V is L-1 of some W says that the vertex operator is the derivative of W. In other words, V is a total derivative. So, its integral over the string worldsheet is the integral of a total derivative and vanishes. And that's the most elementary explanation of gauge invariance for massless states of the bosonic string. Well, what about massive states of the bosonic string? We still need gauge invariance because at the massive levels of the bosonic string, there are a lot of longitudinal or pure gauge modes that we have to get rid of to get a physically sensible theory. But the explanation I've just given does not work. A massive null state might be L-1 of something, but it might also be this kind of descendant, L-2 plus 3 halves L-1 squared of something, where again W is a primary of appropriate dimension. In this second case, it's not true that V is a total derivative on the worldsheet, and there's no reason that the integral over the worldsheet of V should vanish. So why do massive null states decouple? For this, it's really best to use the BRST formalism. So we include the ghosts, and we replace the 1-1 primary V by its BRST invariant cousin, which I call curly V, which is C times C tilde, left and right holomorphic and anti-holomorphic ghosts, times V. So curly V is sometimes called the unintegrated form of the vertex operator. It has ghost number 1, 1. Holomorphic and anti-holomorphic ghost number is 1. And it has dimension 0, 0. And the condition that V was a null vector becomes the statement that curly V is BRST trivial. It's Q of something, where Q is the BRST operator. And W is another vertex operator that actually we can assume to be a conformal primary. Now, in the BRST approach, to compute an S matrix element, we consider a worldsheet path integral. So we take n vertex, if we want to compute an S matrix element of n particles, we take the corresponding n vertex operators, and we take their expectation value in the worldsheet path integral. And then, okay, well, if we literally do that, we're going to get 0 by ghost number counting. To make the path integral non-zero, we need to insert a lot of anti-ghost insertions. So if there were no vertex operators, we would need 6g minus 6 because of an index theorem. But each v had ghost number 2, so we need 2 more anti-ghosts to compensate. So we need this many anti-ghost insertions. And the dependence of the worldsheet path integral on the anti-ghost insertions means that the worldsheet path integral shouldn't be interpreted as a number or a function on the moduli space of Riemann surfaces. Rather, it's a differential form on the moduli space of Riemann surfaces. And the number of anti-ghost insertions we needed is such that this is actually a differential form of top degree on the moduli space of Riemann surfaces of genus G with n marked points. And the genus G contribution to the scattering amplitude, which I denote this way, is then the integral over the moduli space of genus G Riemann surfaces with n punctures of the differential form that we make from the worldsheet path integral. Now, we have to prove gauge invariance. Well, to prove gauge invariance, we suppose that one of the vertex operators is pure gauge. For example, suppose that V1 is Q of some W, where the ghost number of W must be 1 less than that of V1. So it's 1 instead of 2. Now we consider a worldsheet path integral with V1 replaced by W. And the ghost number is 1 less than before. So it takes 1 less anti-ghost insertion than before to make the path integral non-zero. So the dependence of the path integral on the anti-ghosts still makes a differential form, but its degree is 1 less than that of the one we had before. So it has the wrong degree to be integrated over moduli space. Its degree is too low by 1. The essential fact in the proof of gauge invariance is that the BRST operator maps to the exterior derivative in the sense that the differential form with all v's inserted is d of the one with one of the v's replaced by w, assuming that v1 was q of w. So this link between the BRST operator and the exterior derivative on moduli space is what you need to know in order to prove gauge invariance, to prove gauge invariance or decoupling of massive states, massive null vectors of the bosonic string. The proof of gauge invariance is now almost immediate. For the genus G contribution for any G, the genus G contribution to the scattering amplitude by definition is the integral over mgn of the corresponding differential form. But if V1 is Q of W, then as I just told you, the differential form is D of some other differential form. And the integral of D of something is a boundary integral of the something, where what I'm writing as, by the symbol, the boundary of mgn, is informally the boundary of moduli space. When we need to later on, we'll discuss precisely what it is, but anyway, it's the boundary of the moduli space of Riemann surfaces. So the crucial step was the last one, where we integrated by parts and used Stokes' theorem, which told us that the integral of D of something over mgn was the integral of the something over the boundary. Now, the goal was to prove that the left-hand side is 0 if V1 is pure gauge. And we're almost there. We've reduced it to a boundary contribution, which we have to show vanishes. So if, for the problem we're considering now, which is to show that pure gauge modes decouple from the S matrix, there's no great problem in showing that the boundary contributions vanish. So that's how you prove that pure gauge modes decouple from the S matrix. So the moral of the story is that decoupling of longitudinal modes is always proved by integration by parts, but in general the integration by parts has to be made on the full moduli space, not just on the world sheet, sigma. The case where you can make such an argument purely by integration by parts on sigma is exceptional. That only works for the massless null vectors. Now, I'm going to say something which some will find illuminating, and if you don't find it illuminating, just ignore it. The link between the two types of integration by parts comes from the existence of a forgetful fibration from mgn to mgn minus 1. So mgn fibers over mgn minus 1, where the fiber is a copy of the world sheet. So the map forgets one of the punctures, and the fiber is parameterized by the position of that puncture. So you can integrate over mgn by first integrating over the fiber. That means the position of one given vertex operator v1 in a fixed Riemann surface sigma, and then over the base, which parameterizes the remaining moduli of sigma, including the positions of other vertex operators. Now, massless null vectors are the case where we're lucky and we get a total derivative already in the first step. But for massive null vectors, looking at it this way doesn't do us any good. It's only the overall or final integral that gives a total derivative. So this two-step procedure doesn't help for decoupling of massive null vectors. So that's one difference between massless null vectors and massive null vectors. But just as in field theory, there's another big difference between them. Gauge invariances of massive particles are spontaneously broken, so they do not lead to conservation laws. But gauge invariances of massless particles are unbroken, and typically they do lead to conservation laws. So let's talk about that. So, for example, in bosonic string theory, here's a gauge parameter for a massless null vector. So if we take this gauge parameter for W, then Q of W is a vertex operator for a linear combination of a graviton and a B field mode, but it's obviously pure gauge because it's Q of something. So that's what happens. So if K is non-zero but on shell, then this is the kind of gauge parameter we've been discussing already. But if we want to find a global symmetry, we should set K to 0. If we set K to 0, then actually Q with W is 0. In general, Q with W is proportional to K. And if K is 0, W simply becomes BRST invariant. If we set K to 0, then, D tilde is what people usually call D bar, but D bar X is the conserved current that generates a linear combination of momentum and winding of the string. So, assuming we're in flat space, possibly toroidally compactified, which is implicit in writing these momentum wave functions. If K becomes 0, then Q with W becomes 0. So everything we've said before is true, but in addition, V1 is 0. So, okay. So now it's true that the S matrix element with an insertion of V1 is 0 for the trivial reason that V1 is 0 by itself. But on the other hand, the rest of what we said is still true. So this is equal to D of something, and therefore a boundary integral. So now something that's 0 for another reason is a boundary integral. And the right-hand side is not trivially 0. Once we set k equals 0, we find that there are going to be non-trivial boundary contributions in this integral. And the conservation law associated with the massless null vector is the statement that the boundary contributions add up to 0. So in the particular case we've been discussing here of closed strings with the massless null vector that we considered, the conservation law is a linear combination of momentum and winding. If we want only momentum or only winding, we should combine what I wrote with its complex conjugate, with a plus or minus sign. So later in the lecture, we'll come back to analyzing these boundary contributions, but for the bosonic string, that would be overkill. So let's proceed in the bosonic string in a simpler way. So when we discuss space-time supersymmetry, we'll have to return to this way of looking at the conservation law. But for bosonic strings, we don't need such an abstract approach. It's only massless null vectors that are going to give conservation laws, since gauge symmetries of massive states are spontaneously broken. And as we discussed at the beginning, the decoupling of massless null vectors can be proved without all this machinery, just by integrating part by parts on sigma, not on the full moduli space. So let's discuss the conservation law in that language. So for this, instead of saying that it's 0 momentum, Q with W is 0, let's get rid of the ghosts. And then, instead of curly V being 0, it's ordinary V, which is 0. It's 0 momentum. So instead of writing that Q with W is 0, just the derivative of ordinary W is 0. In other words, W is a conserved current, which is anti-holomorphic given how I set it up. Now, when we have conserved currents, to find a conservation law, we do not need any fancy arguments about moduli space. A conservation law in physics, a conserved current in general always leads to a conservation law by standard arguments. I just will remind you of the standard argument. You take a correlation function with an insertion of 0, namely the divergence of the current, and any number of other vertex operators. And then, instead of integrating over sigma, around each vertex operator, I cut out a little hole. I integrate not over sigma, but, we pick up, there are different ways to express the argument. We pick up a bunch of singularities where the current meets one of these vertex operators. One way to express it is that we surround each vertex operator with a little loop. We integrate 0 over the rest of the surface, and then using Stokes' theorem, we write that as a sum of contributions where W is integrated over a little loop around one of the vertex operators. And then if the ith vertex operator has charge Qi, meaning that this integral of the conserved current around Vi multiplies it by 2 pi I times Qi, then we get the usual conservation law that the sum of the Q's is 0, or else the correlation function will have to vanish. So all I've said is that when there's a conserved current, it generates a conserved charge. And for that, we don't need to know anything about integration over moduli space. So in the case of the bosonic string, the global symmetries that are associated to massless null vectors can all be understood straightforwardly without the heavy BRST machinery. Now, one notable thing about this is it always works. If we start with the conformal field theory, that a tree level has a conserved current W, then the argument I've given works on a Riemann surface of any genus. So we've proved that the scattering amplitudes in genus G have the conserved charge. So a conserved current in a conformal field theory gives a global symmetry not just at tree level, but to all orders of perturbation theory. That's not a trivial statement, since, for example, as we'll discuss later, it's not true for space-time supersymmetry. There's no way that a Goldstone boson can come in and spoil the Ward identity. Now let's go to superstring theory. For gauge invariances of massless states that come from the Nevers-Schwarz sector, there's no essential difference. They can be proved by integration by parts just on the world sheet without going to moduli space. And likewise, for the massive states, you do have to go to moduli space. Where there's a difference is in the Ramon sector. Gauge invariances of massless states coming from the Ramon sector, that is gravitinos, are different. Decoupling of gravitino null states and the associated global symmetry, which is space-time supersymmetry, must be studied as one studies the decoupling of massive null states of the bosonic string. That's the main difference between supersymmetry and other symmetries. That the machinery you have to use for space-time supersymmetry is the machinery that ordinarily you have to use only for the massive null vectors. The simplification that in the bosonic string occurs from massless null states does not arise for gravitinos. The reason this is true is incredibly elementary, but it's so elementary that it's easy to overlook. The place on a superstring world sheet sigma at which a Ramon vertex operator is inserted is built into the geometry. The usual way people say this is that the odd coordinate theta of the string world sheet has a square root branch point at the location of a Ramon vertex operator. So you can't move the vertex operator without changing the surface. That's a good description locally. Globally, there actually are some advantages in another description in which you never talk about square roots. Rather, sigma is a smooth supermanifold, but its superconformal structure is degenerate where the Ramon vertex operator is inserted. Even though I think that description has advantages, I don't think we need it today. The fact we need to know today is stated in this sentence. There is no notion of moving a Ramon vertex operator while otherwise keeping a superstring world sheet fixed. That doesn't mean we can't prove decoupling of gravitino null states. It just means that the proper formalism for doing so is the same as the proper formalism in bosonic string theory for proving decoupling of massive null states. We can't prove decoupling of gravitino null states by integration by parts on sigma because there isn't an operation of moving the Ramon vertex operator keeping everything else fixed. So to prove decoupling of gravitino null states, we need to use the heavier BRST machinery that involves integration by parts on the moduli space, not on the world sheet. Now, I have two paragraphs here. One is a summary of what I said about the bosonic string, and then the second is a summary about what I've said about the superstring. And I think each paragraph has 3 sentences, and the third sentence is the same for each, but the beginning is different. So we arrive at the same conclusion, but by a different route. So a vertex operator of the bosonic string can be moved on the string world sheet without changing sigma. But even though we can do that, in the case of a massive null state, it doesn't help. We need a more powerful formalism of integration by parts on the moduli space, not on sigma. So that's a summary of what I said in the beginning about bosonic strings. Now, here are the analogous 3 sentences for superstrings. So a Ramon sector vertex operator in superstring theory, massless or not, cannot be moved around without changing the world sheet. So we can't prove gauge invariance, well, even for massless vertex operators, by integration by parts on sigma. We need a more powerful formalism of integration by parts on the supermoduli space, not on sigma. So the last sentence of the 2 paragraphs is the same, but the reasoning by which we arrived at the last sentence for massive states of the bosonic string or for massless states of superstring theory was a little bit different. But since the last sentence of those 2 paragraphs was the same, what we have to do in superstring theory for space-time supersymmetry is exactly what we have to do in bosonic string theory for massive null vectors. Now, again, this is that funny formula that not everybody will find helpful, but in case you do find it helpful, the fancy way to say it is that the fibration that forgets one puncture, this should be curly M now, up here, has no analog for Riemann punctures on a super-Riemann surface. So there isn't a notion of integrating first over the fiber. You can think there is one if you ignore the supermoduli, but then you end up having to write very complicated papers later on. So we can't prove gauge invariance for Riemann states by integrating over the fibers of such a fibration, as we do for massless but not massive gauge invariances of the bosonic string. Okay, well, roughly 10 minutes ago, I explained how to prove gauge invariance for massive null states of the bosonic string, and now we're going to go over it again and elaborate a few more details with an application in mind to space-time supersymmetry. So every step works perfectly for gauge invariances of Riemann or Nevers-Schwarz states in superstring theory, except that some of the concepts need to be generalized from manifolds to supermanifolds. So we use the integration of forms, the exterior derivative, and Stokes' theorem. So we need to know what the analogs of those are on a supermanifold. But that would be a topic for another occasion. Maybe for now, I'll just say that people who do supergravity, even if they don't say they're using the supermanifold version of Stokes' theorem, certainly integrate by parts. So one way or another, they know such a formalism exists. So as I say, all this, so the stuff referred to in parentheses here is standard, but there isn't time to explain the details today. So for today, just accept that the ideas of differential geometry we use do have analogs on supermanifolds. I'll just repeat what I said before, and we can be talking about either massive gauge invariances of bosonic string theory or the decoupling of a Gravitino null vector. The only difference will be that in the second case, we can go to zero momentum in spacetime and define a global symmetry, which will be spacetime supersymmetry. So let's recall what we said before. If V1 up to Vn are BRST invariant vertex operators, then the worldsheet path integral defines a top form on moduli space. If one of the V's is BRST trivial, say it's equal to Q of some W, then if you replace V1 by W in the worldsheet path integral, you get still a form on moduli space, but it's of codimension 1. The relation between the two is that the top form is D of this form where we use the gauge parameter. That's true in either bosonic string theory or superstring theory. So the proof of decoupling of the null vector proceeds as it did in the bosonic string. In fact, I just copied this from a previous slide, except that I changed the M's into a different font. Oh, I didn't change it here. I tried to change the M's into a different font because, okay, it should also be changed here because everything is now super. But the equation was, as you can see, copied from the previous version. Now, in the last step, we integrated by parts and used the supermanifold version of Stokes' theorem. Now, as before, to complete the proof, we have to show that the boundary contributions vanish. But for decoupling of pure gauge modes from the S matrix, that poses no real problem. For the bosonic string, we only needed this formalism for massive gauge invariances, and they're not related to conservation laws. So for the bosonic string, when we did prove conservation laws, we didn't need this formalism. What's different about superstring theory is that since we need this formalism for some of the massless gauge fields, namely gravitinos, there are conservation laws, spacetime supersymmetry, that do require it. The gauge generator for a gravitino null state is a plane wave, let's say, times a linear combination of fermion vertex operators, where zeta is a C-number solution of the Dirac equation. If we set k to 0, then the Dirac equation is trivial, so we can forget zeta and just take W to be one of the S alphas. Now, everything we said before is true, but in addition, Q with S alpha is 0. So like I said at one point for the bosonic string, since V1 is 0 by itself, this S matrix element is trivially 0, but we can also study it this way and write it as a boundary term. So the supersymmetric word identity comes by explicitly evaluating the right-hand side as a sum over the components of the boundary. So the boundary is the union of components di that represent different ways the surface can degenerate. And I'd like to incidentally thank the staff here for rescuing the fact that this simple picture didn't work in my file before. Anyway, here's a degeneration of the Riemann worldsheet to two genus 1 components with some way of dividing the vertex operators on the two sides. So that's a picture of a typical boundary component. So we get a ward identity. See, the ward identity is that 0 is the boundary integral, but the boundary is a union of components. So what 0 is a sum of boundary integrals of a certain correlation function, where di are the various boundary components. This is a picture of one of the di's. And this is the identity that under favorable conditions leads to space-time supersymmetry. But most of the di's don't contribute. There's a necessary condition that I don't have time to explain now that eliminates most of the di's. So there's one type of contribution that's always relevant, and that's where one component has the supersymmetry generator S alpha and one other vertex operator, and everybody else is on the other side. So the left part of the worldsheet contains the supercurrent, or fermion vertex operator, and just one other vertex operator, V. The contribution of this type of component, you see, you can replace, if you live over here, then what you see is a string state propagating through. And that string state was somehow magically produced by a path integral on the left with S alpha and V. So the sum effective operator made from S alpha and V, that's inserted here. So you get an S matrix element that's obtained by replacing the left part of the worldsheet that contains this product by an effective operator that couples to the right-hand side. This operator is linear in S alpha and V, so we can call it Q alpha with V, or this formula is the definition of the space-time supersymmetry generator Q alpha. If these are the only contributions, we get a conservation law that a bunch of S matrix elements vanishes. Oh, I wrote equals 0 at both left and right, where in each of them we replace V with Q alpha of V. And that's the standard form of a supersymmetric ward identity. But our machinery allows one more type of contribution. You see, space-time supersymmetry holds if and only if these are the only contributions. But there's one more conceivable contribution, which is where on one side there's only S alpha. From a field theory point of view, you'd say that S alpha is producing from the vacuum a Goldstone fermion, and then the Goldstone fermion couples to all these guys. And it's only when there's no Goldstone fermion contribution that space-time supersymmetry holds. So a Goldstone fermion contribution arises in one-loop order in some explicit models that have been studied 25 years ago. The SO32 heterotic string on a Calabi-Yau. So we have a framework in which we can prove space-time supersymmetry when it's valid, when there's no Goldstone fermion, and also understand how it can be spontaneously broken in perturbation theory. The framework is the same one by which one proves gauge invariance for massive states of the bosonic string. The framework carries over perfectly well to superstring theory, once one does a little bit of basic differential geometry of supermanifolds. The fact that in general, the ward identity does have a Goldstone boson contribution reflects the fact that it is not really correct to think of the fermion vertex operator as a conserved current on the string worldsheet. So that concludes my talk, but I have two more things to say. One is to again thank the organizers of String 2013 for their hard work and their hospitality. And beyond that, to say that you're all invited to Strings 2014 in Princeton. Thank you.
Questions? Yes, Sunil.
Apart from the spin fields which you highlighted in your talk, there can be situations with twist fields, for example, when there are orbifolds. These also create branch cuts. So are there any issues associated to moving twist fields on a Riemann surface?
Well, the twist fields only twist matter fields. They don't, from an abstract point of view, a twist field is just a conformal field, a quantum field, whose classical limit might seem unusual. But abstractly, it's no different from any other quantum field. So there are no issues of the type I've described here for twist fields. Thinking of a spin field as a twist field is oversimplified. And that's because of the way the spin fields interact with the geometry. You can get away with it at tree level, but if you try to take that point of view literally in loops, deformalism becomes complicated. I would say that that's what happened in the 1980s.
We'll take one more question.
Just the fact that you say that there is no conservation law associated with Fermi vertex operators, is it related to picture-changing ambiguity in the definition of this of the Ramond vertex?
Well, there is a conservation law in space-time associated with the fermion vertex operator. What I said is that it's a little bit misleading to think of the fermion vertex operator as a conserved current on the world sheet. It's fine as long as supermoduli are not important. But when you get to loops, supermoduli are important. And you run into the fact that the framework of thinking of the fermion vertex operator as a conserved current on a fixed world sheet is oversimplified. I can't remember, sorry, I'm not sure if I answered your question or not. If you ask a follow-up if I didn't answer it.
Actually, I had another, maybe it's a related question. So when you're talking about Stokes' theorem on supermanifolds,
Yes.
In which sense?
You asked about the role of picture changing.
Right.
So picture changing is very central in supergeometry. And I rather vaguely, when we got to the superstring, spoke of integration of forms without telling you what kind of forms they were. Because on an ordinary manifold, you can integrate a differential form, but on a supermanifold, there are things the things that you integrate are sometimes called integral forms. They're not differential forms. You can think of an integral form as a picture change version of a differential form, but that was a topic for another occasion.
Yeah. So, but picture changing operators, it is a not a nilpotent object. So, in which sense you can use the Stokes' theorem in this case?
Well, I'm not sufficiently sure exactly what you're asking, but I'd like to say that there's no problem. And we could we perhaps could discuss it. After all, I've written a very detailed paper explaining these things in detail, but I don't know any quick answer to give you because I don't have a clear enough picture of exactly what you're asking.
Okay.
I think you can discuss later, please. So let's thank Edward again.